Okay, now under today's lecture, we will be moving from what we learned from in the last lecture. So if any of you could remember what are salts, aerosols, forms, can one of you tell me what is a salt? Okay, anyway, if you all can't remember, I will move back and again tell you. A solid is a suspension of small solid particles in liquid as a form of colloid. In the colloid, you have very small particles in the range of 1 to 100 nanometers for inorganic compounds. But for natural rubber, it is around 900 nanometers in diameter. But that is not a solid. Actually, natural rubber is an emulsion. Now, emulsion is a colloid between two liquids. One is immiscible with the other one. Okay, like oil in water, you have two immiscible layers. In these two immiscible layers, if the droplet size is made smaller to colloidal range, you can make emulsions. Then you have form. Form is a gas dispersed in either a solid or liquid. So again, when the gas is dispersed, the bubble size should be very small in the range of nanometers. Then aerosols, those are minute liquid particles or solid particles dispersed in air or gas. So these are the four types of colloidal systems that we know. You know salts, emulsions, forms, and aerosols. Okay, so now as the latex is one of these types, the stability and the destability of latex could be assessed using the properties of colloids. Okay, do you understand? Shall we move on? Okay, so now we'll see what are the properties of colloidal system. Now this one, even though I put this as a first property, heterogeneous in nature, no need of putting it in the, when you write it in the answers. In order to make you understand, I will say it is heterogeneous. Heterogeneous means it is not same in composition. Why I say heterogeneous is, now you have two immiscible parts. Either a solid is dispersed in a liquid or gas, or the liquid is dispersed in air or gas, or vice versa. So now if you have two different phases, that means it itself has a heterogeneity. හැමතැනම එකම composition එක නැහැ. මොකද solid එකක් නම් අපි දන්නවනේ අර molecules ඔක්කොම ළඟට ඇවිල්ලා හයියටනේ molecules දෙන්නේ form වෙලා තියෙන්නේ. උනාට liquid එකකට යනකොට අණු එහෙම නැත්නම් molecules එහෙම loosely bound වෙලා තමයි solid liquid එක හැදෙන්නේ. එතකොට chemical composition එක එහෙම නැත්නම් phase composition එක තනින් තැනට වෙනස්. මේ හින්දා තමයි අපි කියන්නේ heterogeneous in nature. But don't write it in when I ask what are the colloidal properties of natural rubber, don't put this one. But without understanding the properties are heterogeneous, the composition is heterogeneous, you will not be able to move on with it. So you have a dispersed phase and a dispersion medium. So now in a sol, you have, what is the dispersed phase and dispersion medium? What is the dispersed phase and dispersion medium? Okay, for example, if I say a solid is dispersed in liquid, the smaller amount is dispersed. So the solid is dispersed in liquid, means liquid is the major component. Okay, ගොඩක් තියෙන්නේ වතුර හරි liquid එක. පොඩ්ඩයි තියෙන්නේ dispersed phase එක. ඒ කියන්නේ solid එක එහෙම නැත්නම් gas එක. එතකොට පොඩ්ඩක් තියෙන එක we call it dispersed phase. ගොඩක් තියෙන එකට අපි කියනවා dispersion medium කියලා. මොකේද disperse වෙලා තියෙන්නේ? Dispersion medium, in which you are, what is the component that is dispersed in? So it is the solid. So when you think about a sol, what is the dispersed phase? What is the dispersion medium? Ani, you all have to answer me, otherwise you all don't understand. How can I know you all understood or not? Quickly, otherwise we are delaying the lectures and we will not be able to finish it up.
Solid particles.
What is solid particles? Dispersed phase or dispersion?
Dispersed phase.
Okay. Dispersion medium?
Liquid.
Okay, very good. Now, even though the colloidal system is heterogeneous in nature, this is appearing as a homogeneous system. Now, think of milk. Can you see a solid or a liquid particle is dispersed in another liquid particle? Can you see the phase difference? No, right? It is throughout the liquid, you could see it is a solution. So it appears as homogeneous. Again, this one, don't put it in the answers. When you look at the system, you cannot distinguish whether there are two phases coexisting. එකට phases දෙකක් තියෙනවා කියලා අපිට පේන්නේ නැහැ. This is same for all four types of colloidal systems. You could see a single system. You cannot distinguish from your naked eye that there are two different phases are involved in making this system. Understood? Don't write these two properties in your answer script. Okay. In the colloidal systems, even though there are two phases, now in natural system, if you put oil, coconut oil on water, the coconut oil will be floating over water. But when you make a colloidal system, these colloidal systems are stable. This stability is mainly coming from the continuous motion of these small particles due to different charges and also different forces acting on these very tiny particles. Now, when the particle is becoming smaller and smaller, Now, what is the main reason why you're having this separation? That is, either the particles don't like to mix together. This is hydrophilicity and hydrophobicity. As an example, oil doesn't like to stay with aqueous solutions or polar ones, because in polar ones, they like to attract charged materials. But oil don't have this charged behavior. But when the particle become very small, the properties will be much different to the bulk properties. We call bulk properties when it is staying in the normal phase. That means if you have oil phase and water phase, in oil phase, you have different properties than the nanoparticles. So this is why we use nanotechnology in order to obtain very much different properties. Okay, for example, if you have silver, silver is a very good conductor of electricity and heat. Okay, silver කියන්නේ metal එකක් හොඳ සන්නායකයක්. හැබැයි මේ සන්නායක ගුණේ particle එක චූටි වෙලා nano particle එකට යනකොට semiconductor එකක් වෙනවා. හරිද? මොකද මේ වෙන්නේ? අපි සාමාන්‍යයෙන් chemistry එහෙම ඉගෙන ගන්නකොට අපි ඉගෙන ගන්නවා ඉලෙක්ට්‍රෝන වින්‍යාසයයි එතකොට බන්ධන වර්ග එතකොට මෙටලික් බොන්ඩ් එකෙන් තමයි අපිට මේ ඔය සන්නායකතාවය. But when you come to nanoparticles, they are very tiny so that the effect is negligible. Whereas some other effects are coming that will counterbalance. So that is why colloidal systems are always stable when it is made stable. Okay, there are no artificial colloidal systems that are stable, but we can make them stable, like making the particle size reduced to nanometers. Then surface charges will be more dominant than inside the particle. That is why the properties of colloids are much different to bulk properties. Okay, when the particle become very small, you have very large surface area. මොකද චුට්ටි particle එක්ක හැම particle එක්කම ලොකු surface එකක් තියෙනවා. පොඩි particles ගොඩාක් තියෙද්දි surface එක වැඩි. interact වෙන surface එක වැඩි වෙන හින්දා මේ වගේ වෙනස්කම් වෙනවා. So one colloidal property is Brownian motion. Okay, this is first answer for colloidal properties. If I ask you in the question, Brownian motion. The Brownian motion is when you have a particle with a charge behavior. If another same charge come near you, near the first particle, what happened? They repel. So in order to sacrifice, okay, to be safe in this repel situation, these small particles always in continuous motion with the others. So when these small particles are always in continuous motion, repelling from one another, they don't get together and form a bulk solution or bulk phase. තේරුණාද? පුංචි particle එකක් හැම වෙලෙම තමන්ගේ වර්ගයකින් එක්ක repel කරනවා නම් මොකද වෙන්නේ? මේගොල්ලෝ එකතු වෙනවද? නෑ. හැම වෙලේම එහෙට මෙහෙට දුවනවා, එකතු වෙන්නේ නැහැ. හැබැයි එකතු වෙච්ච ගමන් particle එකේ size එක ලොකු වෙනවා. ලොකු වෙගෙන යනකොට මොකද්ද වැඩි වෙන්නේ? particle එක අර bulk properties dominant වෙනවා. එතකොට colloidal system එක destabilize වෙනවා. මේක තමයි colloid එක හැම වෙලේම වෙන්නේ. ඈත් වෙන ප්‍රමාණයට මේක stable. එකතු වෙන්න මේගොල්ලෝ unstable වෙනවා. So this is called Brownian motion. The Brownian motion was first observed by a scientist. I'm not sure the name. I'm sorry, I cannot remember. The Brownian motion was first observed in an experiment regarding pollen. Pollen කියන්නේ මොනවද? පරාග. Okay, when pollen sample is put onto water, you could see this pollen always move in a zigzag position, zigzag way, and they don't come together. No pollen particle will come together to interact with each other. So this Brownian motion is observed under microscope with particles which are very small, and these motions are zigzag path, or we call it random motion. Okay, so first colloidal property exhibit by any colloidal system is particles Brownian motion. Now when you prepare a salt, for example, you have heard titanium dioxide based solar cells. When you prepare the small colloidal dispersion of titanium dioxide in water, when you drop a small titanium dioxide drop on the surface of the titanium dispersion, we can see the drop is bumping on the surface of the colloid, like the stone that you jump on the water. Have you all seen that one? අර පුංචි ගලක් මොනවාද ගඟක surface එකට ගහපුවාම අර bump වෙවි යන්නේ. ඒක දැකලා තියෙනවද? Oh, අහගෙන දින්නේ. Are you all still there, or can't you hear me?
Yes, madam.
දැකලා තියෙනවා. ඒ වගේ චූටි ඩ්‍රොප්ලට් එකක් ලික්විඩ් එකක් උඩට දැම්මහම බම්ප් වෙවි යනවා දැක්කොත් අන්න ඒ වගේ තමයි කොලොයිඩල් සිස්ටම්ස් වල බිහේවියර් එක තියෙන්නේ. දැන් අපි ලැබ් එකේ හිටියනම් මම මේක හදලා පෙන්නනවා. චුට්ටක් ඉන්ටර්නෙට් එකේ ගිහිල්ලා සර්ච් කරලා බලන්න what is Brownian motion. Okay, so because of Brownian motion, the colloidal systems are stable. So remember, first colloidal property that I'm teaching you is Brownian motion. Particles exhibit Brownian motion. Okay. I hope you all taking down notes. The second one, that is main one, another main one, the colloids exhibit optical property called Tyndall effect. Okay, Tyndall effect is when you pass a small light beam through the dispersion, you could see the light beam visible inside. මෙයාට පේන රූපේ බලන්න. mouse point එක පේනවනේ නේද? Okay. Now when you pass a laser beam through pure water, you cannot see the path of the light through the water. මොකුත් පේන්නේ නැහැ. හැබැයි light beam එක pass through වෙනවා. But if you pass a light beam through a colloidal solution, you could see an illumination in the path. So this light beam, you could see how it is moving through the colloidal system. So this effect is called Tyndall effect. Okay, when you keep the colloidal suspension in dark and a beam of light is passed through it, the path of the light is illuminated in usually in blue color if it is laser. This is mainly because the particles are very small. So this light will always interact with the particle and scatter. Whereas in pure water, you have a solution. The particle size is in the range of molecules, not big as colloidal particles, not very small. So the wavelength will not be sufficient in order to scatter. Scatter when the punchi particle එකක් තියෙන්න ඕනේ. දන්නවනේ අපි ලයිට් එකක් ගත්ත ගමන් ලයිට් එක කියන්නේ වේව් එකක්. මේකේ තියෙනවා wavelength එකක්. මේ wavelength එකේ එහෙට මෙහෙට අර උඩට පල්ලෙහාට යනකොට මේක scatter වෙනවා. wavelength එක කියන්නේ intensity එකක්. No, it's an energy, not a particle. Now, in the case of sorry, you cannot see in the true solutions, you cannot see the Tyndall effect. So this is the main reason why latex is appearing in white color. Okay, latex or milk appear in white color because of the Tyndall effect. Make a note. This is fog. As I said before, fog is an aerosol, again a colloidal system where liquid is dispersed in air. Now, when it is really raining, very rainy weathers, when the fog appears, you could see the traffic lights, the path of the light in these ones. Can you see this one? Have you ever seen this one?
Yes, madam.
Okay, when you go to another country in the winter season, this is always you are going to see this one. But in Sri Lanka, as a tropical country, very rarely we can see. But in the case of winter season, most of the time, you will be seeing this type of fog, the light beam in the fog. So this is why we need the fog light in the vehicles when you drive. Okay, normal light is not sufficient. The fog light is for you to see the road. That is why all new vehicles and old vehicles have a fog light. Okay. Now, the particles, as I said before again, the colloidal suspension, you have two different phases. One is small, one is bulk. The smaller one is dispersed phase, which is very small particles. Okay, if it is aerosol or emulsion, you have one liquid in another, so you have a droplet. So that is a particle. If there is a gas bubble inside, again it is acting as a particle, so we call it a particle, right? All particles in a colloidal suspension, we have similar charge. However, the dispersed medium or solvent have the opposite charge, so that the full colloidal system will have zero charge. But this colloidal system, you have whole lot of charge behavior involved in, so that this charges will be acting on one another to make it stable. Okay, there is no net charge. total charge එක බිඳුවයි. එහෙම නැතුව ඇතුලේ තියෙන එකින් එකට තියෙන charges 0 නෙමෙයි. හැම වෙලේම particle එකක් charged colloidal system එකක් ඇතුලේ මේ charge එක හින්දා තමයි colloids add වෙලා තියෙන්නේ. මේක ඔයගොල්ලෝ ඉගෙනගෙන ඇති latex එකේ මොකද්ද තියෙන charge particle එක? natural rubber latex particle එක වටේ charge particle එකක් තියෙනවා. මේ particle එක හින්දා තමයි latex විදියට stable වෙට තියෙන්නේ. මේක කලින් lecture series එකේ ඉගෙන ගත්තානේ. What is it?
Negative.
Yeah, negative charge. What is the particle on the latex particle? You have a minor component now. What is that negative charge coming from?
Proteins and lipids.
Yeah, mainly proteins, not lipids. Okay, proteins will have negative charge so that the latex particles will have net negative charge and water will have a net positive charge. So you have as a whole, you have 0 net charge. Okay. Okay. Now we'll see how these colloidal systems become destabilized. Now, first thing we need to know is the colloid is very small particles are dispersed in another medium. So, if the particle size become bigger, gravity can pull down the particle rather than this net charge behavior on the surface. This charged surface area become lower when the particle size is getting bigger, so that the weight of the particle will be dominated, so that it will precipitate. So this is why mainly destabilization of colloids occur. So what would happen? What would you expect? How do you expect this particle size become bigger? Okay, how do you expect the particles, small particles, to become bigger? තේරුණා නේද? Destabilization will occur when you have this separation of these tiny particles will be lost and precipitate. In order to precipitate, the weight of the particle should surpass the strength of the surface charge behavior. අර එකට එක මං කිව්වේ එකට එක repel වෙනකොට තමයි මේගොල්ලෝ ඈත් වෙලා ඉන්නේ කියලා. මේක repel වෙන්න නම් ලොකු surface charge එකක් තියෙන්න ඕනේ. ඒ කියන්නේ ලොකු surface area එකක් තියෙන්න ඕනේ. ලොකු surface area එකක් තියෙන්න නම් particle size එක පුංචි වෙන්න ඕනේ. මම මේ කතා කරන්නේ total surface area එක ගැන. එක පුංචි droplets 10 චුට්ටි droplets 10ක් තියෙනකොට තියෙන surface area එක ගොඩක් වැඩි. එක මේ droplet 10ම තියෙන mass quantity එක දාපු එක droplet එක තියෙන surface area එකට වැඩි. ඒකයි මේ surface area එකේ වැඩි කියලා කියන්නේ. තේරුණාද? චුට්ටි droplets 10කට යන surface area එක අර එක droplet එකකට වැඩිය ලොකුයි. එතකොට මේ surface එක ප්‍රමාණය අඩු වෙන්න surface එකේ තියෙන charge behavior එක අඩු වෙනවා. surface එකේ charge behavior එකයි surface energy එකයි වෙනස් වෙච්ච ගමන් මොකද වෙන්නේ? බර dominate වෙලා බර හින්දා පල්ලෙහාට යනවා. එක particle එක තියෙන බර surface එකේ තියෙන charge repelling force එකට වැඩි වෙච්ච ගමන් පල්ලෙහාට precipitate වෙනවා. මේක තේරුණාද? So mainly the destabilization of the colloids occur over the time when the particles collide with each other. Collide කියන්නේ එකට හැප්පිලා සම්බන්ධ වුණ වෙනකොට මේක ඉස්සල්ලාම aggregation එක ඇවිල්ලා then it will move into sedimentation. First, the tiny droplets will aggregate together, making the particle bigger and separate as a suspension or separate as the two-phase system. And this is mainly due to neutralization of the charges on the particle. අපි දෙකක් එකට හැප්පෙනකොට ඒ දෙන්නගේ ඇතුලේ තියෙන අර මං කිව්වනේ same type of a particle, they like to tend to mix each other. එතකොට දෙකක් එකට ඇවිල්ලා හැප්පෙච්ච ගමන් ඇතුලේ තියෙන අර like behavior එකකින්දා හැම වෙලේම අපි තමන්ගේ වර්ගයක් කෙනෙක් එක්ක ඉන්න කැමති හින්දා ටක් ගාලා aggregate separate කරලා තියෙන තාක්කල් particles separate වෙලා තියෙනවා. So once this two droplets collide each other, they will become one particle called aggregation. Okay, you can see the small particles are collide each other and combine with each other, making small particles. These are called aggregates. When many of these are aggregated together, the weight will let them sediment. So this is how destabilization occurs. Okay, so we'll move on to the next type. That is when colloids are made, there are basically two types. Depending on the miscibility of the two media. One is lyophilic, one is lyophobic. So in the case of most colloidal systems, these are lyophobic. This first phase is immiscible with dispersion medium. Dispersed phase is immiscible with the dispersion medium. So what type of a colloidal system is natural rubber latex? Lyophilic or lyophobic. Lyophilic is dispersed phase is miscible with dispersion medium. So this type of ones we could see in salts actually, but not in emulsions. Emulsions are mandatorily lyophobic. අනිවාර්යෙන් lyophobic තමයි emulsions. So what type of a colloidal system is natural rubber? One of the boys give me the answer. I heard a girl's voice all the time. Fasan. Fasan, are you there? Fasan is not there. There are 2-3 boys inside in the meeting. Can you unmute and answer, Buddha? I don't like to tell your name. Any of you give me the answer. Any girl or boy, I don't mind. Tell me whether natural rubber is lyophilic one or lyophobic one. Pasindu, are you there? Pasindu? බැරි නම් කමක් නැහැ කියන්න උත්තරයක්. There are 50-50 chance here. No? One is leophilic, one is leophobic. What happened to you? I can't hear anybody.
Leophobic.
Yeah, it is leophobic. As I said before also, natural rubber is emulsion. Emulsion is two liquid systems that are immiscible. So it is always dispersed phase is immiscible with dispersion media. Yes, it is leophobic. So what do we need to learn more? Leophilic ones or leophobic ones? We need to learn more about leophobic. So we'll move on with that one. Okay, so natural rubber latex is leophobic colloidal system. Most important property of leophobic colloidal systems are the stability of these two immiscible phases dispersed in one another. So basically the factors affect the stability are essentially the factors affecting the stability of leophobic colloidal systems. Okay. Okay, now we'll move on to the topic, natural rubber latex. Now, in the natural rubber, we know the polymer is cis-1,4 polyisoprene. So, in the latex, you have this cis-1,4 polyisoprene, which is non-polar polymeric material dispersed uniformly in water medium. Okay, so this cis-1,4 polyisoprene is hydrophobic hydrocarbon chain, whereas water is a polar solvent. So these two immiscible liquids forming a colloidal system. So the latex is an emulsion. So again, I'm telling latex is also a leophobic colloidal system. Therefore, the stability of the latex depends on the stability of leophobic colloidal systems. So I'm repeating again and again for you to remember these words. What is it? You have to know hydrophobic hydrocarbon chain, polar solvent, both are immiscible with one another. Therefore, latex is an emulsion and also a leophobic colloidal system. So if you need to learn about the stability of natural rubber, you need to learn about what are the factors affecting stability of leophobic colloidal system. Now, in your raw rubber manufacturing technology, you didn't need this type of information in order to learn. Now, why do we need this type of information in latex processing technology? That is, you're not going to process the stability to make a raw material, but we are going to put many chemicals into the natural rubber in order to prepare a final product. So for each phase of natural rubber processing, you need to learn how to keep the natural rubber latex stable. How can we do it? In what way you can make it? That is why we are learning this stability systems in different angles. So now, if I ask you why natural rubber is a non-polar hydrocarbon, but dispersing in polar water, it makes a stable system. Okay, if I ask you like that, that means in nature, if one is hydrophobic, one is hydrophilic, they will not mix with each other and make a stable system in nature. අයියේ එකක් වතුරට කැමති නෑ අනිත් එක වතුරට කැමති. Hydrophilic, that means it likes water. Hydrophobic, it does not like water. Bayai වතුරට. But still mix together to form a stable system. So this is බය කෙනෙක් mix වෙලා ඉන්නවද අනිත් එකේ? නෑනේ. ඉතින් මේකක් කොහොමද තියෙන්නේ? So this is what we learn in stability. So this is again, I'm coming back, taking your memory back. Latex is hydrophobic, but it presents as tiny droplets of rubber dispersed in aqueous medium, forming an emulsion. On top of natural rubber latex particle, which is hydrophobic, latex is hydrophobic, but on top of rubber particle, you have non-rubber constituents, namely proteins and lipids. What are the two non-rubber constituents present on natural rubber latex particle? The surface is made out of proteins and lipids. So these proteins are having a net negative charge, phospholipids having positive charge. So where does this larger negative charge is coming? Because of larger amount of protein, and the proteins are very big compared to lipids present, so that the rubber particle is net negative charge. Okay. So overall charge of the rubber particle is negative, and the isoelectric point is 4.7. මේ isoelectric point එකෙන් තමයි අපි net charge එක හොයන්නේ. pH වගේ එකක් තමයි මේ electric point එක. zeta potential measurement එකකින් තමයි මේ isoelectric point එක හොයාගන්නේ. Okay? තේරුණා නේද? isoelectric point එක මොකෙන්ද හොයාගන්න machine එක? Zeta potential analyzer. So this isoelectric point 4.7, which indicates that the rubber particle is negative in charge. හරියට pH එක වගේ pH හතෙන් පල්ලෙහා තියෙනවා නම් acidic, හතෙන් උඩ තියෙනවා නම් basic. ඒ වගේ තමයි මේ isoelectric point එක කියන එකත්. මේකේ number එකෙන් අපිට හොයාගන්න පුළුවන් මේ surface එකේ තියෙන මොන වගේ charge එකක්ද කියලා. Okay, so when you separate natural rubber by centrifugation, you all have learned centrifugation. When you take a field rubber latex and centrifuge, you could see the centrifuge will have 3 regions. Another regions 3ක් තියෙනවා rubber centrifuge කරලා. මේකෙන් තමයි අපි අඳුරගන්නේ we have different non-rubber constituents on latex particles and the latex. Now in the case of, can you all see the screen slide? Slide එක පේනවද? මෙන්න මේක. මොකක්ද මේ? මේ තමයි rubber face එක. ඇයි මේ rubber face එක උඩට එන්නේ? මේකේ මොකද උඩට එන්නේ? ඕ අනේ ඔයගොල්ලෝ කතා කරන්නේ තේරෙන්නේ නැද්ද? Pasindu, do you understand what I'm talking? Any questions? තේරෙන්නේ නැති දෙයක් තියෙනවා නම් අහන්න මට ඔයගොල්ලෝම පේන්නේ නැහැ. So if you have any question, any doubt, you all have to ask and go. Otherwise, no point of doing live lectures. කැමති භාෂාවකින් අහන්න දෙමළ බෑ මට. Either English or Sinhala I can manage. So just ask what do you have? Any doubts you have, you can clarify now. ඔයගොල්ලන්ට ප්‍රශ්න තියෙනවද පසින්දු? Dilshi?
No, madam.
Okay. Now why rubber face is coming top? මේක උගන්නලානේ තියෙන්නේ. ශසන්ත උගන්නවනේ. ඇයි මේ රබර් උඩින් ගන්නවා යටින් වතුරෙන්නේ? වතුරවල density එක natural rubber density එකට වැඩිය වැඩි. එතකොට density එක වැඩි එක යටට යනවා. density එක අඩු එක උඩට එනවා. එහෙමනේ. එතකොට rubber face එකේ rubber කියන එක density එක අඩුයි. So it will come to the move to the top. Okay. So then after that you have the water phase, or we call it serum. Okay. In the top part you have the rubber particles and water. Then you have serum in the second part. Third part, again you have a small white color region that is again similar to rubber phase, but this is actually not rubber phase. This is called leutoids and buffer solutions. So when you put buffers, the buffer will be coming into the bottom. So you have leutoids. Okay, leutoid means you have I will come to leutoids in the next slide. This is present only in the fresh latex, and these are slightly bigger than rubber particles. We usually having carotenoids, acids, mineral acids, salts, proteins, and if you don't do a sensitive centrifugation, some of the rubber particles also comes down, but mainly you can get the rubber part on the top. Okay, so you have to do the centrifugation at lower temperature and in high rotation speed. Here it is 35,000 RPM. So this is how you know that rubber is not a single solution, but having different constituents. When you separate these constituents and analyze, you will get different compositions. Now, in the case of this rubber phase, when you analyze this one, it is not only cis-1,4 polyisoprene present, but it also have certain amount of proteins and also lipids. This is how you say a rubber particle or rubber phase is always having bonded proteins and bonded lipids. This is how the scientists found that there are bonded proteins and bonded lipids on the latex particles so that the pre drop උනේ? Did you all hear me? Can you hear me? Okay, we'll go to destabilization of natural rubber latex. Okay, now when a rubber is in stable situation, you have the particles separated like this. Okay, say under stable dispersion, your rubber particles will be like this, separated from one another. Now, when it comes to instability, early, two or three particles get together and form a small aggregates. Then over the time, the aggregates become bigger and bigger. And finally, it will form a network like this. Unlike in the case of normal colloidal systems, this network type of aggregate, we call it gel. Gelling of natural rubber. Okay, in the beginning, you have a particle separated from one another. In the later stage, you have a gel and you could see a network of aggregate and which forms coagulant in the later stage. Mouse point එක මේ දාපු මේ ඇඳපු ඒවා ඔක්කොම දැක්කා නේද? There are 4 stages of latex destabilization. First one is coagulation. Second stage is flocculation. Third one is agglomeration. Fourth one is coagulation. So we could see the first stage, something like this. This is coagulation. Something like this. Initial stage of instability, we could say flocculation. Later stage of instability, you can say it's as agglomeration. The gel formation, we could say as coagulation. Okay, when you have a stable suspension, sorry. Conservation is coming here. Flocculation is somewhere here. Agglomeration is somewhere here. Coagulation is somewhat here. I don't come in. Conservation is about this one. Flocculation. Somewhat like this. This agglomeration is somewhat this way. Coagulation is called gelling and also coagulation. Understood? Okay. Now, the steel destabilization that you have learned previously is via acidification. Can you all see, can you all remember VFA number you learned? Volatile fatty acid number increases. That means it destabilizes natural rubber latex. Then we could increase destabilization or decrease destabilization by adding a salt, polyvalent metal. For example, magnesium 2+, calcium 2+. If you have these type of polyvalent metals, the destabilization of latex is more or higher. Then any other salt, if you have in higher concentration, again the destabilization may occur. Dehydration, of course, when the water phase is evaporating, the particles will become closer together so that more aggregation will take place. So dehydration also lead to destabilization. Then again, mechanical agitation. ඔගොල්ලෝ දන්නවා ඇති ටිකක් වැඩිපුර හයියෙන් හෙල වුණොත් එහෙට මෙහෙට shear කරොත් latex එක unstable වෙනවා. Other than that, you have freezing. So the latex may destabilize by acidification, addition of polyvalent metals, higher concentrations of any salt, dehydration, mechanical agitation, and freezing. Can I know the time now? ඔයගලන්ට extra lectures දාලා තියෙනවද වෙන subjects වල? Now it's around 10:10. So shall we move a little bit forward so we can cover up the ones that we couldn't do because of the exams last time? Okay, again, can you remember the destabilization factors affecting the destability? Acidification, addition of salts of polyvalent metals. Polyvalent කියන්නේ +1 වලට වැඩි valency එකක්. Charge එක +1 වලට වැඩි. ඒ කියන්නේ magnesium, zinc, copper, calcium 2+, all will destabilize natural rubber latex. Then if you have high concentration of any salt, again natural rubber is destabilized. Dehydration leads to destability, mechanical agitation leads to destability, and freezing will lead to destability. Okay, so this one, when you take first tap rubber tree, fresh latex appears milky liquid. Okay, fresh latex is appeared as a milky latex. Now, when you keep this latex for a certain period of time in this collecting vessel, the latex solidifies and becomes a lump. Then if you keep on leaving the rubber in the collecting cup, it will become discolored and yellowish color lump or bad odor will occur. So what is this? You all have learned this one. What is this process? අනේ නම කියනකම් ඉන්න එපා. Volunteer and answer me. Otherwise, we are getting delayed. Chamira. Chamira, what is this process called? You all did it in raw rubber manufacturing technology lecture module. That is why I'm asking. Fresh latex first becomes solidifies. Then if you keep on leaving the rubber latex in the collecting cup, you will see this yellowish lump with a bad odor.
Recoagulation. Recoagulation.
Okay. Right, very good. This is putrefaction. Matakada. Putrefaction and precoagulation. This is precoagulation. This is called putrefaction. This process occurs due to bacterial activity on natural rubber latex. Now, when you have fresh latex, as we said, there are so many non-rubber constituents. For example, mainly you have proteins, you have carbohydrates, lipids, all these non-rubber constituents that I talk are nutritious. So this medium is very nutritious for bacterial growth. The protein and other constituents will, now the bacteria is growing on the latex, so that this latex, these components will give rise to acidic constituents upon this bacterial activity. And this bacteria will grow. We call it proliferation. Okay, the bacteria will grow in the latex. We call it proliferation and proliferate in latex. So this leads to coagulation. Why it is coagulation? Because it forms more acidic constituents inside latex. These acidic constituents go and break the protein layer on the latex. So if the protein layer is damaged, that means the surface charge is neutralized and the latex particles attract one another, aggregate and coagulate. So this first one, we call it spontaneous coagulation. Then the second step is called putrefaction. Okay. First, the latex becomes a white color solid and becoming a lump. You call it spontaneous coagulation. The yellowish color lump, you call it putrefaction. This lump formation is called putrefaction. Spontaneous coagulation and putrefaction is due to bacterial activity. So this putrefaction and spontaneous coagulation lead to a shorter shelf life of about 4 to 6 hours, leading serious problems to farmers, so that if this is not stopped, they cannot send their harvest to manufacturing companies or factories. So this is why you do preservation of latex in the field. So this step you all have learned. The spontaneous coagulation, okay, the spontaneous coagulation occurs after few hours of tapping. After few hours of tapping, leaving the tree, the spontaneous coagulation occurs. Usually this is, you can see this one starting as rubber clots in a clear aqueous phase. So spontaneous coagulation is the step of this one. In the putrefaction, if you keep on letting this lump to be in the cup, the development of bad odor and that is always with the bacterial activity. Bacterial activity, growing up bacteria will make the latex with bad odor. Now, spontaneous coagulation, usually when you have H+, that is acids, when you have a rubber particle covered with natural the protein, these microorganisms, proteins, sugars and amino acids and acidic substances hydrolyze the protein layer. And what happened to the protein layer? It is broken down. After the protein layer is broken down, the polymer start coagulation. So this spontaneous coagulation usually occurs at the pH of 5. Okay, after pH 5, the spontaneous coagulation is usually occurred. This is mainly due to acidic substances formed due to hydrolysis of proteins, sugars and amino acids by bacterial activity. Make uganala thiyena. Yes or no? This has been taught. Now, if the protein layer is damaged by the formation of H+, then preservation should be removal of H+ from the medium. So what we do is simply adding a base, which is usually ammonia, the best preservative up until now that has been found. So we add ammonia as a short-term preservative or long-term preservative so that formation of acidic constituents will be minimized. And also, ammonia has another benefit, that is because ammonia is bactericide and biocide. So this controls the proliferation of bacteria. Okay, being a base, alkali means a base, okay? Being a base, it neutralizes free acids formed in the latex due to degradation of proteins, sugars, amino acids, and other non-rubber constituents present in latex. Okay? When ammonia is added, it also precipitates magnesium and other polyvalent metals along with sand and dirt. So again, removal of polyvalent ions will make it preserve. And also hydrolyze the interfacial proteins and phospholipids and making the latex more stable, more negative, and the latex medium or the aqueous medium becoming more positive. So this is how you preserve natural rubber latex. Now, if you don't know what are the factors that are affecting latex stability, you will not be able to come up with an answer like this. And also, rather than using other acids, we can use ammonia because this is volatile. So easily we can remove ammonia when you need to make products. So that is another good reason why we can use ammonia as a preservation for natural rubber latex. Okay, this is for homework. I'm not going to assess this one. Write the answer for this one and we'll discuss it next day. For question number 1, natural rubber is cis-1,4-polyisoprene, which is a non-polar hydrocarbon, whereas water is a polar solvent. Despite the polarity difference, natural rubber latex is a stable aqueous dispersion. Name 4 factors contribute to the stability in natural rubber latex and briefly explain one of them. The second part I will teach you next day. Explain the chemical reactions that are responsible for volatile fatty acid development in field latex. Briefly explain how ammonia acts as a preservative for natural rubber field latex. So these 3 questions, do it at home and be prepared next time. If you have any other question, you can ask now. We can wind up after the discussions. Okay, now I will stop the recording. You all can ask me any question after this one. Okay, stop. But anyway, it's good to discuss along with the others so the others will also know. Right. The others will also know, so we'll discuss. Any questions, any doubts? Did you all understand what I was talking? Mahisha?
Yes, madam.
Mahisha.
Yes, madam. No, madam. I'm Mahesh.
Okay, Mahesh. I'm sorry. Mahesh, did anything you didn't understand or any questions you have?
No, madam.
And Dinushi?